We now compute error in Simpson's rule. So, we have expression for error in interpolation when we interpolate the function f of x by a quadratic polynomial. So, it will be the third derivative by factorial 3 into x minus x naught, x minus x1 into x minus x2, where psi lies in the interval x naught to x2. So, we would like to get the error in evaluating the definite integral by approximating f of x by p2 of x. So, that will be integral x naught to x naught plus 2h f of x dx minus this integral p2 of x dx, and we want this expression which is error in Simpson's rule, and that will be integral x naught to x naught plus 2h, the third derivative at psi by factorial 3 into x minus x naught, x minus x1 into x minus x2 integrated with respect to x. So, again by using mean value theorem for integrals, we have the third derivative at some eta by 6 into integral x naught to x naught plus 2h. I use the fact that the points are equally spaced. So, it is x minus x naught minus h into x minus x naught minus 2h, and this must be integrated with respect to x. So, let us consider integral x naught to x naught plus 2h, then this will give you x minus x naught the whole square minus h into x minus x naught, and that must be multiplied by x minus x naught minus 2h and integrated with respect to x. So, x naught to x naught plus 2h, x minus x naught the whole cubed minus 2h into x minus x naught. So, x minus x naught the whole cubed minus 2h into x minus x naught the whole square. Then the next term minus h into x minus x naught the whole square. So, this becomes 3h, then plus 2h square into x minus x naught. So, this must be integrated with respect to x. This will give me x minus x naught power 4 by 4 minus 3h into x minus x naught the whole cube by 3 plus 2h square into x minus x naught the whole square by 2 between x naught and x naught plus 2h. So, we shall apply the limits that will give you at the upper limit x naught plus 2h, this will give you 2h power 4 by 4 minus h into 2h the whole cubed plus h square into 2h the whole square, that is at the upper limit, and at the lower limit all this will vanish. So, giving 16h power 4 by 4 minus 8h power 4 plus 4h power 4 turns out to be 0. So, this tells us that this method is exact for polynomials of degree up to 2. So, let us evaluate the error as follows. Namely, we wanted to see what is the difference between integral x naught to x naught plus 2h f of x dx minus the formula that we derived, namely h by 3 into f of x naught plus 4 times f of x1 plus f of x2. We approximated this integral by this method. So, the error is this minus the method that evaluates this integral approximately. So, it is x naught to x naught plus 2h f of x dx minus, I shall call this as term 2 and this as term 1 and evaluate one by one, and then finally see what the difference is. So, let us first do term 1. It is integral x naught to x naught plus 2h f of x dx. Now, this integral exists, f of x is a continuous function, integral exists, and therefore, there exists a function capital F of x such that f dashed of x is equal to small f of x by fundamental theorem of integral calculus. And therefore, this will be integral x naught to x naught plus 2h capital F dashed of x dx, and that is f of x between x naught to x naught plus 2h, and that is f of x naught plus 2h minus f of x naught. So, we shall use Taylor's theorem and write this as f of x naught plus 2h into f dashed of x naught plus 2h the whole square into f double dashed of x naught by factorial 2 plus 2h the whole cubed by factorial 3 into f triple dashed of x naught plus 2h the whole power 4 by factorial 4 into the fourth derivative at x naught plus 2h the whole power 5 by factorial 5 into the fifth derivative at x naught, and so on. So, you will see why I have stopped with this later on when we also complete the evaluation of the second term. This minus f at x naught, which appears here. So, f of x naught can be cancelled, and this gives us 2h into, I know that f dashed of x is f of x. So, f dashed at x naught is small f at x naught plus 4h square by factorial 2. So, 2h square, f double dashed is small f dashed, then 8 by 6. So, 4 by 3 h cubed, f triple dashed will be f double dashed at x naught plus 16 by 24. So, 2 by 3 h power 4, the fourth derivative of capital F. So, f triple dashed at x naught, then 32 by 120 into h power 5 into fifth derivative at x naught. So, this will be the fourth derivative at x naught plus etc. So, we have been able to express integral x naught to x naught plus 2h f of x dx in terms of the function values and its derivatives using fundamental theorem of integral calculus and Taylor series. So, let us keep term 1 as this. Now, we move on to term 2 and then evaluate what it is. So, term 2 is minus h by 3 into f of x naught plus 4 times f of x1 plus f of x2. So, which is minus h by 3 into f of x naught plus 4 times f of x1 is x naught plus h plus f of x2 is x naught plus 2h. So, I shall use the following notation, namely I shall write f of x naught as f naught, right, and then I expand 4 times f of x naught plus h is f of x naught plus h into f dashed at x naught plus h square by factorial 2 into f of x naught plus h into f dashed at x naught plus h square by factorial 2 f double dashed at x naught h cube by factorial 3 f triple dashed at x naught h power 4 by factorial 4 into fourth derivative at x naught plus etc. That is the first term. The next term is f of x naught plus 2h. So, f of x naught plus 2h into f dashed at x naught plus 2h the whole square by factorial 2f double dashed at x naught, 2h the whole cubed by factorial 3 into f triple dashed at x naught plus 2h the whole power 4 by factorial 4 into fourth derivative at x naught plus etc. I have now collected the terms whose coefficients are f naught dashed and so on, and have simplified and obtained the result at this step, and that is term 2. So, now let us substitute in this expression for the error. So, the error is term 1 minus term 2. So, we now look at the corresponding coefficients. I have f of x naught and I have denoted it by f suffix naught. So, the coefficient of f of x naught in term 1 is 2h and in term 2 it is minus 2h. Then the coefficient of f dashed naught in term 1 is 2h square, that in term 2 is minus 2h square. F naught double dashed is 4 by 3 h cubed minus 4 by 3 h cubed. And then the third derivative at x naught has coefficient 2 by 3 x cubed here, and in term 2 it is minus 2 by 3 h power 4. So, now I write down this term which is 32 by 120, and that is 4 by 15 h power 5 into the fourth derivative at 0, that comes from term 1, and term 2 gives me minus 5 by 18 into h power 5 into the fourth derivative at 0. So, we observe that the first non-zero term in evaluating the error in Simpson's rule comes with the derivative of f, namely the fourth derivative of f evaluated at x naught. So, this is the first non-zero term in the expression for the error. So, this is the leading term in error. This gives you h power 5 into fourth derivative multiplied by 4 by 15 minus 5 by 18. So, that will give you h power 5, so by 90 into fourth derivative. So, 24 minus 25, and that gives you minus h power 5 by 90 into fourth derivative. Since it is something like the remainder term in Taylor expansion, so I write down the fourth derivative at some psi, where psi lies between x naught and x naught plus 2h. So, we see that the error in Simpson's rule is of order of h to the power of 5, and the expression for the error is h power 5 by 90 into the fourth derivative evaluated at some psi between x naught and x naught plus 2h, And what does this tell? This tells you that the method is exact up to polynomials of degree 3. When we computed the error using the expression for error in interpolation, we showed that the term which appeared with the third derivative turned out to be 0, and that is what happened here also. The next term which appears with the fourth derivative survives and it contributes to the error in Simpson's rule. We infer that the error in interpolation is such that the method is exact for polynomials of degree up to 3, and the error is of order of h to the power of 5. And the expression for the error in Simpson's rule is this, namely minus h power 5 by 90 into fourth derivative at psi, where psi lies between x naught and x naught plus 2h. So, what did we do? We derived Newton-Cotes formulas by approximating the function by a linear polynomial and a quadratic interpolation polynomial, and obtained numerical integration methods. And we also have observed that we do incur error in such an approximation. So, the natural question would be to answer, can this error be reduced? Is there a way by means of which I can reduce this error? Can I find a bound for the error in each of these methods? The answer is yes, and we will see how we can do it in trapezoidal rule first. So, the question is how to reduce error in trapezoidal rule. So, can we find bound for error in trapezoidal rule? These are the questions to be answered now. So, what did we do in trapezoidal rule? We evaluated the integral of the function f of x over this interval x naught to x1 by approximating the function by means of a straight line passing through the points x naught, f naught and x1, f1, and h was the step size, which is x1 minus x naught. We evaluated trapezoidal rule as integral x naught to x1 f of x dx, which is h by 2 f of x naught plus f of x1, and the error was of order of h cubed. Or if we can make this h smaller and smaller, then the error can be reduced and we would get better accuracy in evaluating this integral. So, how can we make the step size h smaller and smaller? You simply divide the interval x naught to x1 into, say, a number of smaller subintervals, say of equal width, and then apply trapezoidal rule in each of these subintervals. So, what does that mean? In this interval, I approximate this function by this straight line. In this interval, I approximate the function by means of this straight line, and so on, so that in each of these intervals, you would be approximating the curve by means of a straight line passing through those two endpoints. and apply the trapezoidal rule. So, I shall use the notation that I am interested in evaluating integral a to b f of x dx, and I do it by dividing the interval a to b by means of equally spaced points xi, which are given by x naught plus I h for I is equal to 0, 1, 2, 3 up to n. So, that my points are x naught, x1, x2, x3 and so on, xn minus 1, and b will be xn, and apply trapezoidal rule in each of these subintervals. So, the first interval is x naught to x1 f of x dx plus integral x1 to x2 f of x dx, integral x2 to x3 f of x dx, and so on. The last integral will be xn minus 1 to xn f of x dx. So, when I apply trapezoidal rule, it will be h by 2 into f at x naught plus f at x1 plus h by 2 f at x1 plus f at x2, h by 2 f at x2 plus f at x3 and so on, plus h by 2 into f at xn minus 1 plus f at xn. Because I have equally spaced points, the distance between any two points, namely the upper and the lower limit, will be h. So, I have used trapezoidal rule in each of these subintervals. So, I observe that it is h by 2 into, I see that f naught appears once, fn also appears once, but f1, f2 etc. they all appear twice. So, twice f1 plus f2 plus etc. plus fn minus 1. So, what do I have now? Integral a to b f of x dx is the step size by 2 multiplied by the sum of the end ordinates f naught plus fn plus the intermediate ordinates are taken twice. So, the formula gives me integral a to b f of x dx is h by 2 times sum of the end ordinates plus twice the intermediate ordinates. The resulting formula is what is known as composite trapezoidal rule. The composite trapezoidal rule. So, it is obtained by dividing the interval of integration into, say, n equal subintervals of width h, which is b minus a by n, and the formula gives you h by 2 times the sum of the end ordinates plus twice the intermediate ordinate. Again, the question is, what is the error that is incurred in composite trapezoidal rule? So, that can be obtained by computing the error that is incurred in evaluating each of these integrals in the n subintervals. And we already have determined the error in trapezoidal rule when it is applied to an interval. So, we shall make use of that. So, integral a to b f of x dx minus the trapezoidal rule h by 2 into f naught plus fn plus 2 times f1 plus f2 plus etc. plus fn minus 1 will be equal to the error that is incurred in evaluating the first integral between x naught and x1. What is it? We have this expression minus h cubed by 12 into the second derivative at some, say, psi naught, where psi naught lies between x naught and x1. Then the next interval is x1 to x2. So, the error incurred is minus h cubed by 12 into f double dashed at psi 1 minus h cubed by 12 f double dashed at psi 2. So, between x naught and x1 first term gives the error, x1 to x2 the second term gives the error, x2 to x3 the third term gives you the error. So, xn minus 1 to xn will give you minus h cubed by 12 into the second derivative at some psi n minus 1. So, where this psi I lies between x I minus 1 and x I for I is equal to 1, 2, 3 up to n. So, this is the total error that is incurred in composite Simpson's, composite trapezoidal rule. So, that is minus h cube by 12 into f double dashed at psi naught plus f double dashed at psi 1 plus etc. plus f double dashed at psi n minus 1. So, there exists a psi in the interval x naught to x n such that n times f double dashed at psi will be equal to f double dashed at psi naught plus f double dashed at psi 1 plus etc. plus f double dashed at psi n minus 1, where psi is in the interval x naught to x n. Namely, I can find a psi in this interval such that the average of this, namely the sum by n, will be the second derivative evaluated at psi. So, I use that fact and write down this to be equal to minus h cube by 12 into n times f double dashed at psi for psi lying between x naught and x n. So, this will be minus h cube by 12 into, I know what is n. How did I obtain this formula? By dividing the interval a b into n equal subintervals of width h is equal to b minus a by n. So, I substitute for n as b minus a divided by h into the second derivative at psi, and that gives me minus h square by 12 into b minus a into the second derivative evaluated at psi, where psi lies between x naught and x n. So, the error in composite trapezoidal rule is minus h square by 12 into b minus a into the second derivative at psi for psi lying in this interval x naught to x n. So, we observe that this error is of order of h square, while the error in trapezoidal rule is of order of h cubed. The error in composite trapezoidal rule is of order of h square. So, we have been able to see that the step size h has been reduced, and we have now obtained a formula which is composite trapezoidal rule, so that the given interval of integration is divided into number of smaller subintervals of width h, and resulting integration method has been got, and we have obtained an expression for error in composite trapezoidal rule, and we know that the error is of order of h square. The question now is, can we find the bound for the error in this composite trapezoidal rule? So, what is the bound on the error? It is modulus of E, which is this. So, let us obtain the error bound. So, this will be absolute value of minus h square by 12 into b minus a into f double dashed of psi. So, suppose capital M is the maximum of f double dashed of psi for psi in the interval x naught to x n. then I have E to be less than or equal to h square by 12 into b minus a into capital M. So, I can get the bound in such a way that the error can be made as small as this. This gives me an information as to how many subintervals into which I should divide the interval a b into in order that my error should be less than some prescribed value. Namely, if say I want my error to be less than 10 to the minus 6, then I must have my h to satisfy the condition that h square by 12 into b minus a into m to be less than 10 to the minus 6. Given the integral a and b are known, so I know b minus a, the function will be known, so I can compute the maximum of the second derivative for values of x in that interval and get what m is. So, everything is known in this except h. So, h can be computed. Namely, we know the step size of each of these subintervals. So, when that information is used here, then I know I must divide that interval a to b into n equal subintervals, where n is b minus a by h, where h will come from here. So, the information on the bound on the error tells you, if depending upon what your accuracy is or what you demand for accuracy, you can obtain the number of subintervals n into which this interval a to b can be divided into, so that you arrive at the value of the integral a to b f of x dx correct to the desired degree of accuracy. So, that completes our discussion on the trapezoidal rule, the composite trapezoidal rule, the order of accuracy of both the trapezoidal rule and the composite trapezoidal rule, and how we can get the number of subintervals into which an interval should be divided into depending upon the desired degree of accuracy. So, one thing that remains to be done at this stage is what happens to the Simpson's rule if we perform some similar discussion.